Assalamualaikum Dr. Jundika. We are from group SEARON97 will be present about temperature fluctuation in mixing tea. My name is Haikal and my team member include Azmel, Afiq and Amirul. Without further ado, I will start my presentation with background study. MLNG3 plant in Minnesota use the regenerative gas system to make sure the heating of the fluid flow is uniform. The piping system is designed where the main pipe transport hot fluid and the branch pipe will deliver cold fluid that is resulting in thermal fatigue in the T-junction. Thermal fatigue is the condition where the pipe interior is wearing down, caused by the thermal loading because of stress that induced by the thermal stripping. The critical area in piping that carries two types of temperature fluid is at pipe fitting. In this case, there is a previous report at MLNGT gas plant where there is cracking occur at the weldment around T-junction area. Because of this incident, more experiments need to be done and to investigate the behavior of thermal behavior at the T-junction. Thermal fatigue happens when the material is exposed to the thermal stress cycle that been induced by the random temperature fluctuation and turbulent mixing. The consequences of temperature fluctuation can cause crack network that will cause component failure. This project will be one of the efforts to mitigate the problem that occurs in the pipeline where the mixing region happen, which is T-junction, especially regarding thermal behavior. Our problem segment will be involving with these two mixing T, which is colliding mixing T and intersecting mixing T. As I mentioned before in my previous slide, thermal stripping will be induced thermal fatigue. We also want to observe the behavior of thermal stripping for both mixing T because it is unknown on which is much better in terms of intensity and magnitude. Also, we want to investigate the location of thermal stripping most likely to occur inside the T-junction. Our objective in this project is to evaluate and conduct a comparative analysis for thermal stripping between two different T-junction configuration design, the intersecting and colliding mixing T for MLNG3 regenerative gas piping. So for our scope of study, there is fixed and variable parameter. For fixed parameter, consideration only on the T-junction and not the whole pipeline system. The study is done on the geometry based on dimensions specified and given only. Water as working fluids and transient. For variable parameter, we have three variable parameters, which is operating parameter, geometrical parameter and fluid properties. So for operating parameter, hot liquefied natural gas flow temperature, which is 320 degrees Celsius, cold liquefied natural gas flow temperature, which is 21 degrees Celsius. And for geometrical parameter, T-junction configuration, intersecting T and colliding T. So for fluid properties, as you can see, there is at 21 degrees Celsius and 320 degrees Celsius.
Assalamualaikum and good day. My name is Muhammad Nur Azmi and I will present the next part of the presentation, which is the literature review. Thermal stripping in fluid flow is a result of arbitrary change of temperature fields when two or more fluids with different temperatures are mixed with respect to time. When analyzing this phenomena, the two factors that need to be considered are the amplitude of temperature fluctuations and its frequency of fluctuation. Some studies had been done regarding thermal fluctuation in a T-junction pipe. The first is by Tanaka, Oshima and Monji in 2010. Based on their studies, the fluid temperatures will indicate whether there are thermal stripping happening in the fluid flow. Thermal stripping phenomena is present if the graph forms a sinusoidal wave pattern, indicating there are abrupt increase and decrease in fluid temperatures. Secondly is a study by Selvam in 2016. Selvam's findings suggest that certain ranges of frequency of temperature fluctuation could cause adverse effect on pipe surface, which is in correlation with the study done by Tanaka, Oshima and Monji. Lastly is a study conducted by Kian, Kanemaru and Kasahara in 2015. Based on this study, the fluctuation frequency of interest is below 10 Hz. Our simulation could focus on 0 to 20 Hz and the results from 0 to 10 Hz can be compared for validation. Besides the frequency of interest, they also mentioned that in the mixing T, the highest temperature fluctuation happens at the mixing region and slowly decreases as the flow is heading to the outlet. In addition to that, an unstable flow will also contribute to temperature fluctuation as the mixing will become more rigorous when the flow is turbulent. That is all for the discussion of the literature review. Next, we will proceed to the explanation of the methodology of our project.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Amirul Haziq and today I'm going to talk about the methodology of our project. So this is our overall step in conducting the computational evaluation. We begin with building our geometry, followed by setting up the flow specification. Then we get into modeling methodology. We start with the geometry before we generate mesh. Then we did mesh dependency study before we set initial and final condition, which is the type of inlet and outlet. So for the inlet, we use mass flow inlet, and for the outlet, we use pressure outlet. Then we are setting up the solution procedure and convergent criterion. The convergent criterion value is 1 times 10 power of negative 6, so that we can get more accurate iteration. After that, we ran the simulation and analyze the results by checking the magnitude of the temperature fluctuation, regions of pipe wall where the temperature fluctuations are higher, and characteristic frequencies of thermal stripping. So if the result cannot be accepted, we will go back to the mesh dependency study phase and start all over again. But if the result is accepted, we will validate our result by making comparison with other researchers' findings. So there are three parts, which are pre-processing part, solver part, and post-processing part. For the pre-processing part, we build the geometry of the T-junction, then we specify the boundary conditions, then selecting appropriate meshing criteria and mesh size, and finally select the physics of the model. So for the turbulent model, we use realizable K epsilon as it is adequate to find the temperature fluctuation. Then we came to solver part, where we solve governing equations such as mass conservation equation, momentum equation, and K epsilon. Finally, the post-processing part, where we plot the result based on the simulation by extract the data from ANSYS and plot using Microsoft Excel. So if the result need to be updated, we can go back to the pre-processing part and start all over again. So this is our geometry dimension. Both colliding and intersecting mixing T would have the same geometry and dimension. The only difference is the flow configuration inside the mixing T. For intersecting mixing T, the cold flow will enter the main pipe, which is the horizontal part of the pipe, through the branch pipe, which is the vertical part of the pipe, at D3, while the hot flow will enter the main pipe at D2. Then they will be mixed at the mixing region, which is at the center point of the pipe, and flow to the outlet, which is at the D1 as a mixed flow. So for colliding mixing T, the cold flow enters from D1, which is at the left side, and hot flow will come from D2, which is from the right side. Then they will be mixed up at the mixing region, which is at the center, and flow as a mixed flow towards the D3, which is the branch pipe. So this is our simulation setup. We have scheme, discretization, convergent criteria, wall conditions, transient setting, cold flow, and hot flow. This is our mesh dependency study. So we collect the data by using the parameter function. This table details out the parameters of mesh of different refinements. The maximum pressure was quantified from 7 different element size, and slight difference were produced from mesh to mesh as presented. From the table before, we plot a graph in Excel, and this is our graph look like. So we choose number element as indicated by the red dot line as the result show. The difference quantified in total pressure in mesh 6 and 7 was less than 1%. So therefore, mesh 6 was in good agreement and will be used in the study to reduce computational time and memory use.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afiq Ikhwan bin Zulkifli, and I will present about the validation with numerical modeling for our project. Colliding and intersecting T-junction geometry is modeled to use as model validation with the pressure contour obtained in the research of the Mofter. The result obtained in their studies was computed using the commercial package of ANSYS Fluent and utilized the turbulence model of realizable K-epsilon. The method of solution for the pressure and velocity coupling is simple, with second-order bounded differencing scheme to be used as the diffusive and convective parts of the equation discretization for the model. The dimension of the geometry can be found in the figure given, and the table shown is the parameter and its value to be used in their studies. The results from their simulation were compared and validated with experimental and numerical study conducted by Kuszczak. As you can see here, this is the geometry and the dimension for the intersecting mixing T, while this one is for the colliding mixing T. So next is the validation with pressure contour produced. Our project shows the pressure profile contour and were compared to the Mofter result, and it was clearly seen that the profile obtained were fairly identical to each other. And since the flow pattern is within the acceptable range to the Mofter, the model is applicable to be used for further evaluation in this study. This model will be used for intersecting mixing T simulation. So this one is the validation with pressure contour produced for our colliding mixing T. Similar to the intersecting T, current study shows the pressure contour profile were identical to the De Mofter result. It can clearly seen in the cross-section of the sampling point, whereas each one of the profile is identical to each other. So based on the validation result, our model, which is the intersecting and colliding T, is applicable to be used for further evaluation in the study. So this slide is about the temperature distribution contour that we get for both intersecting and colliding mixing T. As mentioned in the methodology, the cool inlet will have 21 degrees Celsius of fluid, while the hot inlet is at 320 degrees Celsius. The temperature gradient in intersecting mixing T is higher, and consequently, the mixing process is worse as seen in the cross-section of the sampling point. It can clearly seen there is thermal stratified at each one of the cross-section. And at cross-section 1.0D, colliding mixing T shows a better thermal mixing compared to the intersecting T.
The first result of the simulation analysis is the circumferential temperature distribution. For the colliding flow, what can be observed from the graph is that at the first and last 45-degree angle, similar values of temperature is recorded. However, for all sampling points, temperature decreases from 45-degree angle to its lowest value, which is at 180-degree angle, before it increases again starting from 225-degree angle. The variation in temperature observed indicates that thermal mixing happens at every sample points. However, the temperature differences starting from point 0.75D to 1D is significantly lower than at point 0 to 0.5D. Based on the temperature differences, the thermal mixing started vigorous but mixes well as it is further from the colliding point. Next is the intersecting mixing T. The graph produced is noticeably quite similar to colliding mixing T, where the temperatures are constant from 0 to 45-degree angle and started decreasing to its lowest point at 180-degree angle, then increases again from 225-degree angle. However, the line shows no significant variation in thermal mixing as the flow passes through the points. This result indicates that the mixing quality does not improve along the points for intersecting mixing T, whereas the mixing quality in colliding mixing T improved from point 0.75D. To evaluate the degree of mixing quality, the benchmark provided by Choi et al. Can be used to classify whether the mixing quality is good, medium or bad based on the temperature differences for every point. As you can see in the tabulated data, based on only the mixing quality aspect, colliding mixing tea is preferable than intersecting mixing tea, as the mixing quality improves along the sample points compared to intersecting mixing tea. The temperature difference for every sample points are almost constant and does not show any sign of improving mixing quality. The next part will discuss on temperature fluctuations due to turbulence flow.
My name is Muhammad Amirul Haziq, and today I'm going to talk about the result of temperature fluctuation due to turbulence regions. So a transient simulation was done with a total flow time of 10 seconds and a time step of 0.05 seconds for both type of mixing teas. So for this part, three sections are presented, which are 0.25D, 0.5D, and 0.75D, since their turbulent mixings are notable. So based on the figure, we can see the temperature and fluctuation profiles of 0.25D, 0.5D, and 0.75D section of the intersecting mixing T. At the 0 second to 5 second time frame, there were notable fluctuations occur for all the regions. Then the fluctuations start to occur at temperature range of 380 K to 420 K. The temperature fluctuations at region 0.25D is significantly less compared to other regions of the T. So we can say that there is no turbulence occurs at the region since the flow is stratified. So at 0.75D region, which is the green colored line, the fluctuation seems to be happen at time frame of 10 seconds to 15 seconds. These fluctuations are most notable fluctuations and may lead to thermal fatigue. Lastly, at 0.5D region, which is the dark blue colored line, we can observe that there are medium temperature fluctuation compared to the other two regions, with a lower intensity compared to 0.75D. We can observe that there are low intensity temperature fluctuation happen throughout the total flow time. So from the interpreted data, we can say that for intersecting T, fluctuation due to turbulent thermal mixing occur the most at region 0.75D, so there will be high chance for pipe failures to occur in this region. So based on the figure, we can see the temperature and fluctuation profiles of 0.25D, 0.5D, and 0.75D section of the colliding mixing T. So at the 0.25D region, which is the light blue colored line, the fluctuation occur at the temperature range between 430 K to 475 K. For the same section, the most notable fluctuation occur in the time frame of 5 second to 10 second, 10 second to 15 second, and 15 second to 20 second. So this fluctuation may lead to thermal fatigue. From the observation at the 0.5D section, which is the dark blue colored line, the temperature fluctuations are greater. This section's intensity is the highest since the minimum temperature are at 410 K before it start to increase to the maximum temperature, which are at the 480 K region. So from the observation, we can say that for 0.5D section, fluctuation due to turbulent thermal mixing occur the most, and therefore the pipe failure are highly to occur in the region. So for the 0.75D region, which is the green colored line, the temperature fluctuations are not as high as other sections. By referring to the turbulent regions in colliding mixing T figure showed, the turbulent intensity is lower in this region. This the reason why fluctuations are lower here. So in this region, good thermal mixing T has also been achieved. So by comparing both of the graph, we can conclude that there is higher intensity of fluctuation occur in the colliding mixing T overall.
So this is the temperature fluctuation for magnitude against frequency. So this graph represents the intersecting T for magnitude against frequency. So as you can see, the result at 0.25D are presented as fluctuation intensity is higher in this region. High magnitude at frequency of 0.92 Hz, which is for intersecting, and for colliding at 2.17 Hz. This is similar to the claim, which is between 0.1 to 10 Hz. This graph represents magnitude against frequency of colliding T. Result at 0.25D for colliding T and 0.75D for intersecting T are presented as fluctuation intensity is highest in these regions. High magnitude at frequency of 0.92 Hz for intersecting and for colliding at 2.17 Hz. This is similar to the claims, which is in between 0.1 to 10 Hz. So that's all for me. Thank you.
As a conclusion, a numerical simulation of turbulence flow of two streams at different temperature was conducted to analyze the differentiation in the intersecting and colliding mixing T. Turbulence model of realizable epsilon was used in this project, and comparison was made with the previous work, which state that the current project results are sufficiently accurate. Even though most of the literature review are using similar turbulence model in conducting their researches, it is widely recommended that the large eddy simulation is much preferable in simulating a turbulence flow model. The different flow configuration in the mixing T resulting different thermal mixing behavior, whereas the colliding mixing T provide a better mixing quality compared to the intersecting mixing T. Despite the quality of the thermal mixing, colliding mixing T proved to have higher intensity in terms of temperature fluctuation when in comparison to the intersecting mixing T. Since the temperature fluctuation intensity is much higher, the magnitude of the fluctuation tends to become high. Therefore, thermal stripping and high cycle thermal fatigue tends to occur more often with shorter period of time when compared to the intersecting mixing T. Hence, the objective of this project is achieved. So that's all from us. Thank you for watching.